The law of cosines and Heron's formula. Hey, it's me again. This video actually combines two different topics, but because we're dealing with the side case of triangles where you know all three sides, I just thought this was really awesome to put together. So before I jump into law of cosines, a triangle, in this case, side scenario, three sides are known, none of the angles are known. So when we solve this triangle, we're trying to find out what each measure is. Now, some students that are okay in trig, they always tell me, well, I'm just going to use the law of sines every single time, and if I can't, then I'm going to use the law of cosines. But we can't use the law of sines in this one because we don't know any of the angles. By that I mean, if we say the sine of A is to 10 as the sine of C is to 8, we have two missing values and only one equation. So, that's a little difficult. Something else I'll point out is that, well, we'll just wait for that little fact. I will say, just make sure you know the law of sines, you know the law of cosines, and the law of cosines is nothing more than a special case of the Pythagorean theorem. I wrote it 3 different times. C squared equals A squared plus B squared. That is the Pythagorean theorem. And then what we do is we take away twice AB times the cosine of C. And look at the pattern here. It's the same formula. It really is. You're not trying to memorize 3 formulas. You're only trying to memorize one. The law of cosines, a special case of the Pythagorean theorem. And keep in mind, we have the law of sines and the law of cosines because we don't have a right triangle. So keep that in mind. 2 of the primary reasons why we have the law of sines and law of cosines is we don't have a right triangle. Though if you were given a right triangle, you could use these laws with it, but it would be kind of crazy too because we have some old hippie called another hippie tripping on apples. So all that good stuff. So let me just go ahead and run through this real quick. So in this case, I want to find the measure of angle C. So I know that C squared is the side length opposite, so that's 64, 8 squared. A squared would be 10 squared, which is 100. B squared is 12 squared, which is 144, minus 2 times A times the length of B, which is 12, times the cosine of C. So doing this very quickly, we've got what? 244 minus 10 times 2 is 20 times 12. We can do this pretty daggone quick in our head, can't we? Yes, we can. So this is 240. So times the cosine of C. I've got my calculator handy just in case we don't want to make any boo-boos. I'm going to subtract 244 on both sides. So that gives us negative 180 equals negative 240 times the cosine of C. And now I'm going to divide negative 180 by negative 240. And we're going to get 0.75 times equals the cosine of C. So since we're looking for the angle, we're going to type in second cosine of 0.75. And I get approximately, I'm just going to round this really loosely, 41.4 degrees. Beautiful. Let me try it again with this one. I'm going to try to find angle B measured. So keep in mind, angle C right now we're saying is 41.4 degrees. Now I know what you're saying, and you should be. Wait a minute. Now we've got side angle side. Can we use the law of cosines? Do you think about that? Now, you can't use it for side, angle, side. Now, angle, side, angle, or angle, side, side, we could use the law of sines, but be careful for that ambiguous case, which is why a lot of times students want to do this once and then jump straight to the law of sines. My recommendation is go ahead and use law of cosines again. It's pretty simple. Look at this. B squared, which is 144, equals A squared, which is 100, plus B squared, I do apologize. I think I wrote that incorrectly, haven't I? Yes, I have. This should be C squared. I do apologize. Notice how I can catch my own errors. B squared equals A squared plus C squared, and I'm looking, these should be the same variable. So, sorry about that. Good catch. Thank you. Thank you. I'm glad you did that. So, C squared is 8 squared, which is 64, minus 2 times A. A again is 10. C is 8 times the cosine of B. So this gives us 144 equals 164 minus 2 times 8, which is 16, times 10, 160, times the cosine of B. I'm going to subtract 164 on both sides and get negative 20 equals negative 160 times the cosine of B. I'm going to divide negative 20, which is really easy to do. These are beautiful numbers. This is 0.128 equals the cosine of b. I divided both sides by negative 160. And now second cosine of 0.125 is giving me an angle measure of 82.8 degrees. So b equals 82.8 degrees. 82.8 degrees. Let me make that 8 a little prettier. Now I know what you're thinking. 180 subtract these two will give it to you. Abso-smurfly. But what I'm going to do is go ahead and do it one more time, show you the law of cosines. So once again, a squared is 10 squared, which is 100. B squared is 12 squared, which is 144. C squared is 8 squared, which is 64, minus 2 times b, which is 12, times c, which is 8, times the cosine of a. So very quickly, this is 100 equals, come on, 44 plus 64. That's pretty easy to do in our head. That's 208. So 4 plus 4 is 8, 6 plus 4, beautiful, minus 2 times 12 times 8, which we can do in our head, that's 192, that's simply 12 times 16, times the cosine of a. I'm going to subtract 208 from 100. I'm going to divide by negative 192, and I get 0.5625 equals the cosine of a. So second cosine of that 0.5625 gives me 55.8 degrees. So A is 55.8 degrees. So if we put 55.8 degrees, let's see if all three of these add up to equal 180 degrees. 55.8 plus 82.8 plus 41.4 gives me exactly 180 degrees. We solved this triangle beautifully using the law of cosines 3 times. But once again, keep in mind, you could have done it one time, then use the law of sines, and then you could have used it a second time. You could have just used the fact that the 3 angles of a triangle add up to equal 180. Law of cosines, special case of the Pythagorean theorem. So we know what these angle measures are. We could put them over here, and it would actually help us solve this triangle a lot quicker to find the area of it. Heron's formula. We want to find the area, and this formula is really awesome when we're dealing with the side scenario. When we know all 3 lengths of a triangle, we can find the area of it using Heron's formula pretty quickly. My recommendation is to go ahead and take a 3, 4, 5 or 6, 8, 10 right triangle, and which you can use 1/2 base times height, base and height of the legs of a right triangle. Pretty easy. But in this particular case, you could use Heron's formula just to verify that, with triangles that you already know how to find the area of. This one, don't know what the area of it is, but it's not a right triangle. The 3 sides do not satisfy the Pythagorean theorem, and we know it wasn't a right triangle because none of these are equal to 90 degrees. But since this one's pretty doggone close, I reckon you could say that 8 and 10 could be the legs, so 1/2, 8 times 10, so we're looking at an area of around 40 square feet for this one. So let's see if we're close, because it is close to being a right triangle. So what we do is this. S is simply the semi-perimeter. In other words, the perimeter divided by 2. So in other words, 8 plus 12 plus 10, that's pretty simple, that's 30 feet. That is the perimeter. So divide it by 2 and we get 15. So Heron's formula, I'm not going to prove or derive it right now, but all I'm going to say is how simple this formula is. All we do is say 15 times 15 minus a, doesn't matter which one you let be a, so I'll go 15 minus 12 times 15 minus 10 times 15 minus 8. And what we get is 15 times 15 minus 12 is 3. 15 minus 10 is 5. 15 minus 8 is 7. So the area of this triangle is nothing more than the square root. And I could actually, this would be really fun to break it down. What I'm going to do, I'm going to do 2 things with this one because it's just so much fun to do. This is 15 times 3 times 5 times 7, which is the square root of 1,575. And the square root of 1,575, wow, is 39.7 square feet. And as we said, this angle was real close to being 90 degrees, which meant that these two are real close to being legs of a theoretical right triangle. So 1/2, 8 times 10 would have been 40, and daggone it, the area of it is pretty doggone close to 40. Now, if you want to do this another way, and this is actually kind of fun, instead of multiplying these together, 15, well, wow, that's just 5 times 3. I've already got a 3 and a 5. And then I've got 7 right there. So the square root of all of this, the exact area, remember this is an approximation, the exact area would be 5 and 5, bloop, 3 and 3, bloop, 7, oh. So this is nothing more than 15 times the square root of 7, which is 39.7. So this is the exact value of it. You know, breaking down this, I mean, keep in mind, you know, 5 times 5 is 25, and the square root of 25 is 5. 3 times 3 is 9. 9, the square root of 9 is 3. 5 times 3 is 15. That is the exact area of that triangle. So the side scenario, you're given all 3 sides of a triangle. Law of cosines, pretty awesome. Heron's formula, sometimes known as Hero's formula in some textbooks, but this one's pretty awesome too. And you'll see this formula again if your Calculus 1 instructor loves pulling this stuff up and, you know, playing with it a little bit, especially maximizing and minimizing areas and so forth. It's really good stuff. Watch this video again. Law of cosines, Heron's formula. Side, side, side.